Okay, the topic for today's lesson will be orthogonal sets. First, let's begin with a definition. I trust that everybody knows the meaning of orthogonal. Orthogonal means perpendicular. So orthogonal sets of vector means we are considering the vectors which are perpendicular to each other. In another word, the dot product of two vectors, any two vectors from the set will be orthogonal. Okay, here is the definition. A set of vectors u sub 1, u sub 2, all the way up to u sub p in Rn is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. That is, dot product of any two vectors, any two distinct vectors from the set equals 0. So that's the definition. Now here is example 1. Let u1, u sub 1, u sub 2, u sub 3 is given by these three vectors. Is this set an orthogonal set? Why or why not? So all you need to do is u1 dot u2. I want you to find the dot product of these two vectors. Find u1 dot u3. Find u2 dot u3. Okay, different combination. Let's see. u1 dot u2. So that means -1 4 -3 dot 5 to 1. Again, never forget to write the dot there in between these two matrices. Otherwise, the product of this matrix does not exist. The only dot product exists, okay? So when you dot these two, you're going to get -1 times 5 plus 4 times 2 plus -3 times 1. And that's going to be, yeah, that's 0, okay? Let's try this. u1 is -1 4 -3, u3 is 3 -4 -7 equals -1 times 3 plus 4 times -4 plus -3 times -7, which is equal to, how much is that? 21 and 16, 9 is 19. So -19 plus 21, that is 2, which is not equal to 0. So since you notice that the dot product of these two vectors not equal to 0, you don't have to do this now. They are not orthogonal to each other. So the set is not an orthogonal set. In order for this to be orthogonal set, every combination, the product of distinct vectors u1, u2, u1, u3, and u2, u3, all of them should be 0. Okay, so this is not an orthogonal set because of this, because u1 dot u2 is not equal to 0. That's the reason. Done. Any question? All right, now let's look at this theorem. This theorem is about orthogonal set and basis. Okay, if S has a bunch of vectors there, u sub 1, u sub 2, all the way up to u sub p. Remember that when I'm talking about vectors here, then I'm talking about the one column matrix. So one column matrix is vector for this case, okay? And is an orthogonal set of non-zero vectors in Rn, then S is linearly independent and hence is a basis for the subspace spanned by S. By the way, if this is what this theorem is telling us is that if this is a orthogonal set, meaning dot product of any two vectors equal to 0, then these vectors are automatically linearly independent. You don't have to consider the augmented matrix and check whether there is any free variable or not. You can do that, but that's a lot of work. You don't need to do that. Okay, once you know that the vectors are orthogonal to each other, then the set is automatically linearly independent, and therefore basis for the subspace generated by these vectors. Okay, here is the definition now. An orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. By the way, the proof of theorem 4, just in case if you want to look at the proof, then I'll provide that in my lecture note in Canvas. So you can have a look there, okay? And here is another theorem. Let u sub 1, u sub 2, all the way up to u sub p be an orthogonal basis. This is orthogonal basis, meaning all these vectors are orthogonal to each other. For a subspace of W of Rn, for each y in W, the weights in the linear combination y equals c sub 1 u1, c sub 2 u2, all the way up to c sub p up is given by this formula. Okay, the formula is c sub z equals y dot u sub z over u sub z dot u sub z. J runs from all the way up 1 all the way up to p. Now, using this theorem, let us solve this problem. Okay, I think with the help of example 2, you understand clearly what this theorem 5 is trying to say. Okay, just by looking at this, if it makes sense to you, great. If it doesn't make sense to you, then just wait few minutes. With the help of example 2, I think you will get the point what that theorem is trying to say. Okay, u1 is given and u2 is given. There are two vectors given and form an orthogonal basis of R2. We need to show that, we need to check whether this form an orthogonal basis for R2. Okay, let us look at that. Orthogonal basis means these vectors must be linearly independent. Remember, to prove the basis, we have to show two conditions. Remember from chapter 1. Condition 1 is the vector must be linearly independent. Condition 2, it must span. It must create the space, generate the space, so span the space, okay? So first thing first, u1 dot u2, 2, negative 3 dot 6 and 4, which is 2 times 6 plus negative 3 times 4 equal to 0. So yes, they are orthogonal. And so since u1 u2 is an orthogonal set, u1 u2 are linearly independent and span R2, because there are two different vectors, linearly independent vectors, and in R2 and span R2. So u1 u2 form an orthogonal basis for R2. Okay, so we prove that. In order for this to be basis, it has to it has to satisfy two conditions. Condition 1 is linearly independent and orthogonal. Because they are orthogonal, they are linearly independent and span R2. Just for basis, just these two conditions. For orthogonal basis, then the one more condition we have to add, which is the vector must be orthogonal, and we have checked that the vectors are orthogonal. Okay, it satisfies all these three conditions. Okay, for basis of orthogonal, I think we need to add one. The vector must be orthogonal and linearly independent and span. We have seen that both. Now, if S, write x equals 9 and -7 as a linear combination of u1 and u2. Okay, let us write that. Let x equals, it's a linear combination, c1u1 plus c2u2. Okay, where c1 is given by, look at the theorem. Theorem 5 tells us c1 is given by this formula. If it is y is the linear combination of that, then c1 will be y dot u1 over u1 dot u1. So here we have x, so that means we can write c1 equals x dot u1 over u1 dot u1. This is your c1, and c2 will be, by using the same formula, x dot u2 over u2 dot u2, by using that theorem. Okay, so let us calculate this. What is c1? By theorem 5. So x is 9 and -7 dot u1 is 2 and -3 over u1 is 2 and -3 dot 2 and -3. I want you to calculate that, and then c2 will be 9 and -7 dot u2 is 6 and 4 over 6 and 4 dot 6 and 4. And I want you to calculate this. So on the top, you get 9 times 2 is 18 plus 21. 18 plus 21, is that 39? Over 4 plus 9, that is 13. And which is actually 3. This side will be 54 minus 28, which is 26 over 36 plus 16. 36 plus 16 is 52. So you're going to get half. Okay, so x can be written as c1 is 3 u1 plus c2 is half u2. So we can write this way. Now let us check whether it makes sense or not, whether they are equal or not. Okay, let us check just for fun. So 3u1 plus half u2 equals 3u1 is 2 and -3 plus half u2 is 6 and 4 equals, you're going to get 6 and 9, -9 plus you get 3 and 2. So if you add them together, you're going to get 9 and -7. Is this x? Let me go all the way up. What is x? 9 and -7. Okay, guys, we got it. 9 and -7. This is x. Okay, that's what it is. So what we did here is that we splitted x into two vectors which are perpendicular to each other. And this is called orthogonal decomposition of the vector. If you want, let us look at this graphically, just for fun, okay? What is going on? Okay, what we notice here is, if we want to see this graphically, let me draw the graph. So my first u1 vector is, vector u1 is 2 and -3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9. Okay. So your vector u is 2 and negative 3. So that's going to go here. This is your 2 and negative 3. This is your u1. Okay, this is your vector here, u1. And u2 is 6 and 4. So 1, 2, 3, 4, 5, 6, and 4 is all the way there. So this is your u2, which is 6 and 4. This is your vector u2. Okay, and let us draw x. X is 9 and negative 7. So x is 9 and the down value is negative 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 7 is 1, 2, 3, 4, 5, 6, 7. Somewhere 1, 2, 3, 4, 5, 6, 7, 8, 9 right there, and 1, 2, 3, 4, 5, 6, 7 right there. So this will come all the way here. This is your vector x, okay, which is 9 and negative 7. So what we did here is that if you want to decompose this x, now this part 3u1, so let me write what is 3u1. What we did is we decompose x into 3u1 plus half u2. That's how we decompose. 3u1 means 3u1 is 2 and negative 3 plus half u2 is 6 and 4. So that's going to give me 6 and negative 9. So basically we increase that by 3 times. So all the way here. So this point is 6 and negative 9. So you can check that 6 and negative 9. This point. So what kind of point is this? This is called the orthogonal projection. So suppose if you have a torch light, okay, and then you are projecting this point over this line. Later we define this as y hat or x hat for that matter. Okay, we'll define this as x hat in a minute. But this one is basically the orthogonal projection. This guy here is orthogonal, perpendicular. Okay, it's the projection of that point over this line. So you have a torch light. Once you put the torch light there, you will see the shadow of this point over here. It is just like shadow of x. Okay, shadow of x on the direction of u1. In the same way, notice that this part right here is 3 and 2. So 3 and 2 is 1, 2, 3, and 2 is right there. So this is the point which is 3 and 2. So this point is, notice that this is simply the orthogonal projection of sorry guys, this is somehow disconnected. Just let me share that again. Oh, come on, what happened?